So algebraic complexity deals with the question of, I mean, the best way to compute certain polynomials. So polynomials, of course, they occur a lot in symbolic computation. I mean, you want to compute determinants, solve a system of linear equations, etc. Everything boils down at the end to computing some polynomial, usually multivariate polynomials. And the most natural model for those computations is the model of arithmetic circuits. So let me start with definition. Okay, so what is an arithmetic circuit? Okay, so maybe just, okay, arithmetic or... So it's algebraic circuits or arithmetic circuits. So maybe I'll just give an example before giving the definition. So basically, it's an analog of Boolean circuits where instead of the Boolean operators, you use the arithmetic operators. So for example, you can have something like this, like, and then, I don't know, x1 plus 5, 2, etc. Right? Some graph where you have variables and constants at the bottom, and then you start computing. You take sums, you do products, etc. So formally, the definition is as follows. So an arithmetic circuit is a directed acyclic graph. Okay, so the graph, you can think about the directions going up from the bottom up. So acyclic means that, right, there are no cycles, so the computation is clear. No. Okay, so in degree, so I have this habit of using my hands instead of the, so vertices of in degree 0 are called inputs, okay, and are labeled with, so either a variable, we have, let's say we have n variables, I goes from 1 to n, or they can also be labeled by some element from an underlying field. Okay, so the circuit depends on the field, right? So I should have said it at the beginning, there is some field in the background. Maybe I should do that. Okay, there's some field in the background, and we work over that field. So the same polynomial, for example, if you think about a polynomial that have only 0, 1 coefficients, then we can interpret that polynomial over any field, and the arithmetic circuit for that polynomial may depend on the field. And then computations will also be done in the field. Anyway, so vertices of in degree 0 are called inputs. So in degree 0 meaning no edges come into those vertices. So these are the inputs, right? Okay. And conditions are labeled with this. So non-inputs are labeled with either plus or times. Okay, like here. Yeah, and we can also ask about divisions. We will later speak about why we don't use divisions. We'll say that actually it doesn't matter that much. Okay, so we have the nodes are labeled with with the arithmetic operators. The inputs are labeled with variables. Yeah, but by the way, please ask questions. I mean, it will not be very. I mean, the crash course will be quick, but it should be clear also. So ask questions if you don't understand. Oops, sorry. Okay, so this is a circuit, and we said that a formula. Okay, so this is called a circuit, and a formula is a circuit whose graph is a tree. Or, in other words, the out degree is at most 1. Okay, so, for example, this is a formula, but this is a circuit, because that node branches into two things. Okay, so this is a circuit, and that's a formula. Okay? So this is similar to what you've seen in Boolean complexity. I mean, if you've seen Boolean circuits. Yes? Not necessarily. We allow arbitrary in-degree for now. In some cases, we will restrict it to be 2 just for the sake of the argument. But it will not matter that much because, right, if a multiplication gate is a large high degree, you can just build a tree, right? That will do, I mean, you can just, something like this, you can just put like something here, then something here, and then do this, right? So we can easily move between in-degree 2 to large in-degree. So, okay, so I don't want to restrict the in-degree right now. That's a good question. Okay, so what are the complexity measures that we associate with arithmetic circuits? So one measure is the size of the circuit, which for now, let's say it's the number of edges in the circuit. Okay, and there's the depth of the circuit, which is the length of longest input-output. Oh, I didn't say what an output node is. Every node can be an output node, right? Okay, we'll say how the computation is done, but you can think about, okay, so basically it's the longest directed path in the circuit, okay? So for example, in this example, it will be 1, 2, 3, 4, 5, yes. Depends on, okay, if you count edges or vertices, it doesn't matter, okay? Right, so what is the computation, right? So the computation is done in the natural way. What do I mean by that? So a variable computes the polynomial. That is, this is the polynomial that is the constant function 5, and that's the polynomial x5. Okay, and then at the multiplication gate, you just multiply the 2 polynomials at your children, etc. So in the natural way, let's natural way. Input poly on their label, etc. Okay, so I'm not writing the full definition, but I think it's clear, right? The inputs are labeled with a polynomial, either a constant polynomial or a variable, and then there's this, a simple dynamics, right? You just compute the sums and products of your children. We will usually speak about circuits with one output gate, and so it will usually be the top gate, but we also allow multi-output circuits, so several gates or output gates. Okay, so this is the definition of arithmetic circuits, and that will be the model of computation that we'll basically deal with throughout this workshop and the bootcamp. Okay, so what are the natural questions that we wish to study that are related to arithmetic circuits? So the first natural question is understanding the complexity of certain polynomials. I give you a polynomial. How large or what is the best circuit computing this polynomial? And what do we mean by best? Can be the smallest circuit computing the polynomial, or if you want to compute the polynomial in parallel, what's the, shortest depth in which you can compute the polynomial and still have reasonable size, etc. So understanding complexity of polynomials in the AC model. That's one question we'll be interested in, and especially proving lower bounds. Now, what do I mean by proving lower bounds? Proving that, say, for some polynomial, that any arithmetic circuit for that polynomial must have many edges. Okay, so what is many? So the polynomial will have a certain number of variables, say n variables, and we would like to say that many edges has to be at least some polynomial or even super polynomial or maybe exponential. Okay. Another question that we will look at in this workshop is the following, simple question, understanding whether two circuits, compute the same polynomial. So I give you two computations, and I ask you, do they compute the same polynomial or not? You can also ask it in a different way. I give you some computation, does it compute a zero polynomial or not? Right? Just deciding whether what you have is the same or different, that seems very basic. And that question is known as the polynomial identity testing problem. Okay, and another question that we will not deal with so much in this workshop, but it's still very interesting and it's there. It's trying to learn an arithmetic circuit. So imagine that there is some arithmetic circuit inside the box, and what you see is that you can give the box an input to the circuit and get the value of the circuit on that input. So you feed in an input, you get an output. You feed an input, you get an output. And from those collection of examples, you want to reconstruct the circuit inside the box. Right, so reconstructing okay, so the three problems, the proving lower bounds, understanding the polynomial identity testing, and reconstruction of arithmetic circuits are the main questions in this area. And when I say understanding the complexity, it's not just proving lower bounds, it's also coming with new algorithms, right? Like, yes?
So does this model have any connection with the Boolean world?
That's a good question. So, yes and no. So this is a weaker model in some sense than Boolean world, because what happens here is that if you think about it, so arithmetic circuits are defined over a field f, right? So the polynomials that they compute, you can think about them as polynomials over the field f. So they can take values from f and output the value of the polynomial, right? If this circuit computes some polynomial, when you plug in values for the variables and you do the calculation, plus, times, etc., you'll get the output of the polynomial on that input. But if you think more what happens here, it acts on field elements, right? It gets as input field elements and it output a field element. Boolean circuits, on the other end, don't get a field element, right? They get the bit representation of that field element. So they can do more things than just, you can simulate an arithmetic circuit with a Boolean circuit, right? You can just say that, okay, a field element will be represented by a string of bits. No, you can do additions and multiplication with small Boolean circuits. But you can do more stuff, right? You can change the order of bits, you can shift bits right and left, you can do stuff with it that arithmetic circuits cannot. So we don't know what this extra power gives us. We don't know. But in principle, Boolean circuits can do crazy stuff that arithmetic circuits cannot. Or maybe they can, but it will be of very large complexity. So like, just imagine taking some integer, representing it in binary, and then switching to digits. To write an arithmetic circuit that does it, it's already something, right? It takes, in Boolean, it's a trivial operator. So yeah, there are connections, but later on we'll also define an analog of the P versus NP question, which is provably simpler, in the sense that separating P/poly from NP/poly would imply results for the arithmetic world, but we don't have the other way around. So, okay, it relies on the generalized Riemann hypothesis, but even if you assume that we don't have results from the other direction. So, if you want to attack P versus NP, start with the arithmetic world, because it's supposed to be simpler. And yeah, okay, yes. Number of edges and the number of nodes. It can be at most squared. If we bound the fan-in to be 2, then it's most 2, right? So, yeah. So counting edges and counting nodes if you only care about polynomial blow-up, then it doesn't matter. And sometimes edges would just be simpler to work with. Okay. Yeah, and another important thing to note is that in Boolean complexity, what we care is about computing a Boolean function. Right? You just want a circuit over the Booleans. So a Boolean circuit is like an arithmetic circuit, except that you use and, ors, and nots instead of the arithmetic operators. And in the Boolean world, we don't care about computing a polynomial, but rather on computing a function. So, for example, in the Boolean world, if you put x and x, it's the same function as x, right? Because you take x and x is always x, right? So as Boolean functions, these two guys are the same. But on the other end, as polynomials, if you, okay, maybe that's not, yeah, this is a multiplication, this is a variable. So, but in the arithmetic world, this computes the polynomial x square, and this computes the polynomial x. And as polynomials, x square and x are not the same polynomial, right? A polynomial basically is a list of coefficients. So if the two lists are different, it's not the same polynomial. So as a Boolean function, these are the same function, but we care about computing polynomials. Okay, so the arithmetic computation is a syntactic computation. You don't care about the semantics, what are the values over the small field, but you care about getting the exact coefficient for the monomial. Okay? So that's a very important distinction. And because of that distinction, we'll see results in the arithmetic world that are not known nor believed to be true in the Boolean world. For example, we'll show that arithmetic circuits can be parallelized very efficiently. This is not believed to be true in the Boolean world. So the arithmetic, this structure that we compute, that we care about syntactic computations, and that we worked with field elements rather than bits, makes a lot of difference, and this is why, I mean, I'm also more optimistic that separating P from NP would be possible in the arithmetic world, or at least, if you believe that it will happen in the Boolean world, it will first happen in the arithmetic world. So, okay. Good, so now let me define the main complexity classes that are associated with arithmetic circuits. So, like in the Boolean world, we can also define analogs of P and NP to define what are efficient computations, etc. So let me define the class VP, which is VP. So V stands for Valiance, who first defined those classes. I mean, of course, he did not name them Valiant P, but this is the common name now. Okay, so I want to define this class. So first I will define, so like in the Boolean world, you work with languages, right? A language is a subset of 0, 1 to star. So in the arithmetic world, you work with a family of polynomials, okay? So a family of polynomials, Fn, right, over a field F, is what? P computable, right? P bounded. P stands for poly. Okay, so a family of polynomials is P bounded. If there exists a polynomial, so this is like a size measure or something. Let's say S. Okay. So when I want to say that the family is P-bounded, I want to say that, okay, the nth polynomial has polynomially many variables in N, its degree is polynomial in N, and its circuit complexity is polynomial in N. So I just take one polynomial to represent all those things. So if there exists a polynomial, so there's one polynomial such that, so the number of vars in Fn is at most S of n, the degree of Fn, at most S of n, and the arithmetic circuit complexity of Fn is at most S of n. So by that, I mean that there exists, for each n, there exists an arithmetic circuit that computes Fn. So again, what does it mean compute? It means that when you do all the computations, you get a polynomial at the end. It is the same polynomial as Fn, exactly the same polynomial, right?
Amir?
Yes.
Do you distinguish between x squared and x even if the field is the binary field?
Yes. So it's a syntactic computation. I don't care about the function. And if you're bothered, you should think about a polynomial over a field F that should work also for every extension field or for the algebraic closure. And then x1 and x are of course different, right? So really we care about syntactic computation. Yes. Okay, so this is a definition of a peer-bounded family, and VP is the class of all peer-bounded family. Okay? So this is like, it's a similar definition to NP, right? In NP you define a language, I mean, as a Turing machine that runs in, there is some polynomial that for every input length, Turing machine halts after that many, polynomially many steps, etc., and accepts the input. And this is an analogous definition. So let's see some examples. I don't know, say Fn of x equals x1 times xn. Just trivial, right? Something trivial. This is clearly a family in VP, right? This polynomial S is n, right? You have n variables, the degree is n, and here is an arithmetic circuit of size n for that polynomial, right? So this is an easy family in VP. Perhaps a more interesting family that will play an important role soon is the determinant of an n by n matrix. So by that I mean that X is a matrix of variables, right? Of Xij is a variable, and so the determinant polynomial. So writing down the determinant is not as easy as writing down this polynomial, right? Because the determinant is n factorial many monomials, right? It's just as a reminder, it's summation. So Sn is the symmetric group of n elements. S1 to the sine of sigma. But we have efficient ways of computing the determinant. You've probably seen Gaussian elimination. So Gaussian elimination doesn't seem like an arithmetic circuit because it uses divisions, but the determinant has efficient arithmetic circuits. If you want as an exercise, you can try to think about the following over the rails. Can you see the exercise? So the determinant of a matrix is the product of the eigenvalues, right? If you have, I mean, over the real set, over the complex, it's product of the eigenvalues. So it's a symmetric function in the eigenvalues. And we know that the basis for the symmetric, there are several different bases for the space of symmetric functions. One base is that if you have the lambda 1 up to lambda n are your eigenvalues, and you know the summation of the lambda i's, and the summation of the square of the lambda i's, and the summation of lambda I cubed, and summation of lambda I to the 4, etc., from 1 to n, if you have all those traces, right, some lambda I square, etc., then it gives you a basis for the space of symmetric polynomials, and every other symmetric polynomial is a polynomial in those, and there's actually an efficient formula to represent each, I mean, you know, basically there's an efficient formula to represent the product of the lambda i's from those things, and just if you think what is the trace of x to the d, it's basically summation of lambda I to the d, right? So say that lambda said that the matrix is diagonalizable. So if you write everything, then you get a polynomial. So you can use Newton identities to get a circuit that doesn't use divisions for the determinant from those traces. I mean, take it as an exercise, just because many people don't see it. So yeah.
What is X is a symbolic?
Yes, and this is lambda i's. I mean, yeah, I mean it's yeah. This. I mean, I didn't see what the lambda i's are. There are, of course, complicated rational functions, etc. But good. So basically, you can express the traces like that and use Newton identities and get a circuit for the determinant. Anyway, this is just an exercise. I mean, don't worry about that. Okay, good. Maybe I'll show you one more family which is efficient. And the last example will be maybe let's call sigma nd. So it's going to be the symmetric polynomial on n variables of degree d, just summation. You just take all multilinear monomials of size d in n variables. Okay, so this is a symmetric polynomial, and this polynomial too, I mean, if d is large, it has many monomials. Say if d is n over 2, then it has n choose n over 2 many monomials. But still, we have a very efficient way of computing it. And actually, let me show you the circuit for computing this polynomial, because it's also perhaps a bit surprising. And yeah, okay, so to show how to compute this polynomial, consider the following auxiliary polynomial, g of y equals pi of y plus xi. Okay, y is a new variable, right? Just it's like a thought experiment we are doing now. So what is this polynomial? If you expand it out, and it's summation of y to the n minus k, sigma n k. Right? So basically, the polynomial that we wish to compute is one of the coefficients in G. Right? This polynomial is a coefficient of y to the n minus t. Now, how do you get a coefficient of a polynomial? So later we'll show it, I mean, I will actually do it explicitly, but this is a polynomial of degree n in y, right? So by evaluating it on n plus 1 points, I can interpolate the polynomial, right? If you have a polynomial of degree n in one variable, you evaluate it on n plus 1 points, and then take some combination of the evaluation points. You can get every coefficient you can get is a linear combination of those evaluation points. So basically what we'll do, we'll compute g at 1, g at 2, up to g at n plus 1, or maybe start with 0. So what each computation gives you some constant plus xi and the product of this thing. So this expression is a very small circuit, right? It's a circuit, right? So basically the circuit will look like, at the end you'll have a plus gate that takes all the evaluation into consideration. Then you have product gates, and say the kth product gate, it will compute k, it will have plus here. This will compute k plus x1 up to k plus xn. Okay, and then we'll have some linear combination of those. Okay, so there will be also some constants, some coefficient alpha 1 up to alpha k, etc. And then the linear combination will give us sigma and d. And basically for every d, you can just take different elements in your linear combination and get the output. We will later do it more slowly, but you'll see it, but that's basically what you do. You just interpolate a polynomial. And it's a bit interesting because, you have many, many monomials here. They seem to be far from each other, yet you can compute it very efficiently, very quickly. Yes? Yeah, I mean,
but the point is that this one, this second
yes,
is
depth efficient. Yes, so that's okay. So that was, I'm just going to say this, but not the induction. So as Michael said, if you just want a circuit, yeah, you can probably do induction on n because, right, you have to compute all the monomials without the nth variable, then xn times sigma n d minus 1, and then my induction, you write down stuff and you get it. But what is special about that circuit, and that's what I was coming to, is that if you think, what is the depth of that circuit? It has only depth 3, right? We don't restrict the fan-in, right? So we have depth 3 circuit. So it's a bounded depth circuit for computing this symmetric polynomial. And if you've seen it, probably not everyone have seen it, but some of you may have, if you think about Boolean complexity and look at bounded depth Boolean circuits, and think about so what would be an analog of this polynomial? It can be the threshold function or the majority function, right? A symmetric polynomial over the Booleans. Then those polynomials require exponential size Boolean circuits if you restrict the depth, not just to 3, to any constant. So it's a huge difference between the algebraic world and the Boolean world. And in this strange example, it's the algebraic world in which things are easier. And the reason is that, well, okay, bounded depth is a very restrictive world, and the fact that the field is large, right, I needed n plus 1 different points to do this interpolation. So this was crucial. And in the Boolean world, we don't have n plus 1 points, we have only 2. So you cannot do interpolation. So that's a special example where things can be done more easily in the arithmetic world. Okay. Well, I already managed to forget the schedule. So the talk is until 10:20, the first talk? Okay. Okay, so that was the definition of VP. Yes? No, and we are coming to that. I think not. I don't know how to prove it, but... No, so for example, over GF2, we don't, okay, over very small fields, this is probably not possible. There is a lower bound that I don't think will prove it, or maybe, probably will not show it. But if the field is small, like independent of n, then you can prove an exponential lower bound for computing this polynomial or some other analogs of it. So you really need room to move around. In depth tree, yes. No, so I mean, by induction, for example, it's very easy to do that. But well, okay, sorry. Formula. So this is a formula. It's a
finite field.
Finite field. I mean, with unrestricted.
Unrestricted depth formula.
I think the induction should give something. What the formula? I think you should be able to do it with a small formula, right? By induction.
You can definitely simulate a large field.
Yeah, but yeah, and larger. Yeah, it's possible. Yeah. Sorry. Yeah. So for formulas. Yeah. Okay. So maybe formulas. There's still something to prove, but over small fields, right?
Can you comment about why is the VP bounded by the degree bounded by?
Why do we bound it? Okay, there was a question, why do we have this bound on the degree in the definition of VP? So basically, if you don't bound the degree, so there are two, I mean, first of all, if you don't bound the degree, it's the same as Boolean model in some sense, because given, let's say over a small field, or having a bit is just a function of the input. So you can just write a complicated polynomial that will give you each bit of the representation, and then you can work with bits. So there's no difference, say, at least over small fields. But perhaps a better answer is that let's look at the following polynomial, say x to the 2 to the n. So the degree here is not, let's say, I mean, x1 even, okay? I mean, say we have n variables, but I don't care about the rest. Right? So the degree is exponential. Clearly, there is a small circuit for it, right? Because you just take x1 and then you just do, iterative squaring, right? So there is a very small circuit for it. So it satisfies everything that we say about p-bounded except for the degree. Now, the point is that let's think what will happen if we will try to simulate this with Boolean circuits. So let's say that we walk over the rational or something like that, and or whatever, the integers, and we plug in some input. The input will have a bit length, say, what is the bit length? It's like if you write the input in binary, it will have L bits. So it's a number between 1 to 2 to the L, say. So the output, so it's a very small circuit, but for writing the output, you will need exponential representation. So what you would like a model in which writing the outputs also does not take exponential. So for this, we also bound the degree. So this maybe, yeah. So these two explanations, I think allowing unbounded degree, it gives you too much power in some sense. So it doesn't, give you enough separation from the Boolean world. And secondly, that if you want to simulate this, then exponential degree just require maybe exponential. The bit length of the output can be exponential. Whereas if this was a polynomial degree, then you can prove that the bit length of the output is polynomially longer than the input. So it makes sense to have such closure properties. Okay, so as you know, for every p there's an np, and for every vp there's a vnp. So let's define vnp. Yes?
If we try to use Gauss elimination to get, apart from the division issue, there will also be this issue of checking if things are 0.
Yes. So, right. So, okay. We're getting into points I didn't want to get to, but so what Brinal said is that when you have a matrix and you do Gaussian elimination, you have to check whether you divide by 0 or not. But what you can do is the following. Because we compute polynomials, think about this matrix as variables that none of them is 0. Okay, just formal variables. And then do Gaussian elimination. So you can also always divide, because you assume that you never divide by the 0 polynomial, just as a thought experiment, okay? So you get a circuit that uses divisions, and indeed for certain inputs you'll divide by 0. But let's ignore that, because you divide by some formal polynomial. Now later we will show how to get rid of divisions. And then we'll get a polynomial that as polynomial is the same polynomial as the determinant, and then it will also work for, because we will get rid of divisions. So you can write a formal circuit that uses divisions that in some cases may divide by 0, but it divides by formal polynomial, so you're not worried. Then you get rid of divisions, and then, yeah.
Is also exponential.
No, it's not.
Yeah, if you simulate simply Gaussian elimination, it will be exponential. Then you have to.
No, it will not be. I mean, it depends how you do it, no? I think, okay, but we have simple circuits for, yeah, I mean, anyway. Yeah, I mean, maybe if you divide iteratively.
The usual one will get exponential symplectically.
Yeah, okay. Okay, maybe. So that's not how I do determinants. I mean, I don't compute determinants, my students do, so. Yeah, so do it for me, yeah, so. Yeah, I mean, let's not worry about those issues, okay? That's, I mean, it's not, yeah, so delicate questions like this, we can take it offline, okay? So let's move forward. But trust me, you can take it as an exercise, determinant as small circuits. Okay, so now let's define the class of VNP. Okay, so the definition may seem a bit strange at first, but let's think, what is NP? So NP, you start with a language in P, right? But in which the input is divided, right? You have some, I mean, okay, what's NP? So what is NP? So you have a relation, xy, so that when given x and y, you can decide in P whether x and y satisfy the relation or not, right? And then a language is in NP, right? Let's say that you have a language L, which is all the pairs xy such that xy is in the relation, right? And what is the language in NP? That's a language in P, right? L should be a language in P. And the language in NP will be this L prime, which will be all the x's such that there exists a y such that xy is in L, right? So basically what you do is you start from an easy function, and then you add like an OR, right? A big OR that there exists a y. So you do OR over all y's, right? It's basically the OR of all y's. I mean, you can think about it as, I don't know, L prime of x. Let's say the characteristic function. If you want to compute the characteristic function of L prime at the input x, it's just the OR over all y, the characteristic function of L of xy, right? That's basically what you do. So you have this huge OR over something in P. So the analogous definition in the arithmetic world will be the following. So a family Gn is said to be P definable, right? That's P bound and that's P definable. If there exists some, let's say T, some polynomial. So again, T will be the complexity, and basically you can think about it as T bounds the relation between y and x, right? You want the widthness in NP to be polynomial in the length of the input, right? Poly T and P bounded family on Fn such that, okay, so G n of x, yeah, maybe I need two polynomials. So first of all, I want to say that, okay. So the widthness, maybe you can call it W for widthness. So the widthness will be of length polynomial in the input length. And then, okay, so what happens here? Let's do it slowly. So first of all, the polynomial T just connects Gn to Ft of n, right? Maybe it's not 1, 2, maybe the n polynomial goes to the n square polynomial. Okay, it's not a big deal, as long as this transition is polynomially long. And then you have a polynomially long widthness. Now, instead of doing an OR over all widthnesses, you do the sum over all widthnesses. Okay? So the widthness goes from 0, 1. Okay, so if you think about, so this family is in VP. So it means that it has a circuit. So basically you can imagine that you have a circuit and you have two kinds of input, the X and the Ws, and then you evaluate the circuit on all 2 to the K to the N value input, 0, 1 inputs to the witnesses and sum, and take a huge sum at the top. Okay, so that's the value of Gn at the point X, and clearly it is a polynomial, right? Because every F is a polynomial. K of N. K is the one of the, oh, S, sorry. Sorry. Yeah. Yeah, Ft of N. So Ft of N, yeah, it has a certain number of, I don't know. I mean, yeah, I just write it very generally. I mean, maybe I should have written F of N and, you know, have witness and inputs, everything N. But basically, that's the idea. And so that's a family that is P-bounded. So again, the analog, I mean, the intuition should be that this sum replaces this O. Okay, that's the intuition. Instead of doing O over witnesses, you take sum over witnesses. And then VNP is the class of all P definable families. Yes, if there's this polynomial, this okay. Such that this is a thing. That's the such that this happens. Gn is P is definable if you can find a family in VP such that this is satisfied.
Just assign 0, 1 values.
Yes, just 0, 1s. You don't need more than that. Yes. Okay. Okay, so this, I don't know whether it's less natural than NP or as natural or more natural. It's different, but it's similar. Okay, and let me show you a function in VNP. Yes. Just maybe Fn is not n, it's n squared. Just some, yeah, maybe I'm doing it too formally, but yeah. Basically, if you can reduce from G to F, I mean, it's not really a reduction, it's not a reduction, but basically, everything should be polynomially related. That's what I want to say, okay? Okay. P-definable families. So we just define the family to be P-definable, and it's like a language, right? It's the set of all languages for which, yes. Okay, so I'm erasing that board, and I want to show you a polynomial in VNP. So let's see an example. So the polynomial in VNP that I have in mind is the permanent polynomial, which, so the permanent is also a polynomial on n by n matrices, and it is defined as follows. We do summation over all permutations, but without the sign. Right, so it's a very delicate difference for the determinant. In the determinant, you also have plus minus here, depending on whether the permutation is even or odd. Here you don't. And this little, I mean, it makes the permanent look easier, right? You don't have negations. But somehow, sometimes negations help. And the permanent, I'll show you how to compute it as a VNP polynomial. We don't know whether it's in P. We believe it's not in P. And we later see that we'll define reductions between families of polynomials. We will show that under those reductions, the permanent is actually VNP complete. Okay, so that's the, say, analog of 3-SAT or something like that. Okay, so what is the circuit for the permanent? So let's write Reiser's formula, which is basically an inclusion-exclusion formula for computing the permanent. So it's summation over all subsets of n. Right, I mean, how would you go to compute the permanent, right? Basically, you have the matrix x11, x1n, 1, xnn. You have to compute the product over all generalized diagonals, right, over all permutations. So one natural way to start would be, okay, take the sum of the first row up to the last row and multiply them. So in this way, you get all monomials, right? but you also have monomials that you don't need. Which monomials we don't need? Those monomials, okay, so we have one variable from each row like that in every monomial, but we may get several variables from the same column, right? So we have to subtract those variables. So we have to subtract those variables that are supported on, say, n-1 columns, etc., etc. So this is really inclusion and exclusion. So that's what we have here. So we have -1 to the n minus size of t, and pi to n summation of j. So basically, when t is the whole set, t is the full set n, you just take this sum and multiply it. Then you subtract, you just pick n-1 columns and you multiply those, you take the sum on, say, on those columns, and you multiply those sums, and you subtract it, and you do it for every set of n-1 columns. But then you subtracted the monomials that are supported on n-2 columns too much, so you add them, and that's exactly inclusion exclusion. So this does not look like that, but it's not very different. For example, you can write it as, so, okay, let's introduce new variable, summation of y, 0, 1 to the n. Now, here we should have -1 to the n, I guess, times y minus 2yi. So think about y as the characteristic vector of the set t. I will be 1 if I is in t, it will be 0 if I is not in t. Okay, so -1 to the size of t should be that, right? Whenever yi is 0, you don't get anything. Whenever it's 1, you get -1. And then the product will just be summation of yj xij. Okay? And that's it. That's in VNP. Why is it in VNP? Because we have a summation. Okay, maybe I'll. Okay, we have summation over all 0, 1 inputs of something. What is that something? If you think about this, this is a very, very simple family of polynomials, right? It's just product of sums, right? It's a product of sums, right? So it's a very shallow circuit even, right? That's it. So that's a VNP representation of the permanent. Okay, and maybe before taking a break and more coffee, I'll just mention the problem that you can take as an exercise for the break. That's variance hypothesis. That's VNP. Okay. Okay, let's take a break.